Okay. Just making sure everything's being recorded. Hello, I'm Dr. Michael Keiderling. Uh, I will be teaching you astronomy, descriptive astronomy, Astronomy 201 this semester. The best way to contact me is my email, which is mkeiderling@ccc.edu. I do have office hours. My current, though they may change, but the current schedule I'm planning is that. Your name? Sorry? Let me just quickly. Jocelyn Garcia Bahena. So my current plan for office hours is that I will have office hours here immediately after class. And then I also will have office hours from 12:50 to 1:20 at Daily Campus, because I teach a class at Daily Campus. So I'm only going to be here at AVI at this campus Tuesday and Thursday mornings. Well, also Fridays, because I tutor on Fridays here. But so I also am available in the tutoring center in person and remotely via Zoom, because I work there. So I'll have some hours on Tuesdays and Thursdays. I think it's 3 to 5. That'll be a daily, and then I work on Fridays from 9 to 4 here. Those just got set like yesterday, so. The textbook is free. It's online. It's OpenStax Astronomy. There's a link on Brightspace directly to the textbook. So if you go to the Brightspace, you go to content, everything is in content. You go see here. Syllabus, textbook, and schedule. This is a direct link to the textbook. It's at openstax.org, books, astronomy. There's also a link to each individual. I think I put correct links to each individual chapter in the folders for each chapter. You can buy a print copy if you want. There's no requirement, but they're available for not too much money. But I mean, it's free online. And you can download a PDF if you want to download a PDF, or you can just use it on the website. So if you go to the website, this is what you get, and you can go to the table of contents and choose a chapter. Your name? Okay. Oh wait, I didn't need to do that. Just quickly, Ruben. Ruben, you said? Oh, I have you marked in already. Were you here earlier? Your last name? Lombo? Why you don't seem to be on my list? You could just note your name down for me. Just so I can you get added later. Make sure it's me. Okay. So that's where you can find the book. You can find the syllabus for the class on Brightspace, right up here at syllabus in the standard simple syllabus format that we're all using now, starting this semester. So that has all the basic information about the course. So, credit hours, where it meets, my office hours, and the schedule. So grades in this class. There are 4 portions. We're going to have exams. They will be in class, multiple choice. And there's going to be 4 of them. And that'll be 40% of your grade. So you have 4 exams. They will be curved. There are worksheets, which are online homework assignments on Brightspace. They're a mixture of multiple choice and short answer. They're all just up on Brightspace. You don't need to use any online homework software. I just made, I think they're called quizzes on Brightspace, but they're just homework. There will be 4 large homework assignments, 1 for each test, basically. We have 4 sections. And each homework assignment is a set of questions from the book. So it's a list of questions from the book. You need to answer them, turn it in. You can either turn it in on paper, hand it in class, or you can turn it in digitally on Brightspace. And lastly, there will be a semester project for the end of the semester. That will be 15% of your grade. It will consist of a 2 to 3 page short paper and a 5 to 10 minute PowerPoint presentation on a topic of your choice. And there's a list of topics you can choose. The topic is due after the first, about halfway through the semester. But you can turn it in early if you want. No, topics are first come, first served. But you can make your own topic if you don't like any of the ones in the list. I don't have a problem with that, as long as it's recent. The list is just, I grabbed a bunch of possible things you could use to help. So you don't have to think what up. But the way it works is when people go back to content, if you see here the semester project, in the semester project section, there will be a list of claimed topics. So you need to choose ones that aren't on that list. If this ever opens, jeez. So here's a list of the list of claimed topics. As you can see, it is currently empty. But as people send me topics and I okay them, I'll add them to this list. You'll get some points for having turned in your topic. And there's a list of, these are example topics here that you can look at. So we're going to do a series of chapters. We're going to do like chapters 1, 2, and 5 through 7, roughly. We'll have a little bit of chapter 3 in with chapter 2. But I put that in the slides. And then we'll have an exam on those, then we'll do the next set of chapters, 8 through 12, have an exam on those. And then your topic is due after that. Then the next set of chapters, exam on those, then the last set of chapters, and an exam on those. All the grades will be up on Brightspace. Your homework and worksheets are all here on Brightspace. They're split for each chapter. They're split into like a true, false, and multiple choice and a short answer section one. And that is simply because Brightspace can automatically grade true, false, and multiple choice questions. Short answer questions, I have to grade. So I've set it up so that you get immediate feedback on the short answer and multiple choice questions. You can you can submit worksheets many times a week. So if you get the multiple choice, you get a terrible grade on the multiple choice questions, you can go through and do it again, and that'll improve your grade. I do accept late work, but there is a penalty for late work. And then the homework is problems from the book, which you can either submit on Brightspace, or if you don't want to, you can just hand it to me and I'll grade it. So this is our schedule. It's a little small here, which is why I was showing you from there your names. Anderson. Anderson and what? Victoria. Okay. So this is the schedule. So the lectures will be in person here. If possible, that is pretty much always, as long as there aren't technical issues. Lectures will be recorded and posted to Brightspace so you can review them. This one is being recorded. The lecture slides are already posted to Brightspace. The only ones I need to update are these, because I have the ones from the last time I taught this class. So dates and announcements and stuff on them might be off, but otherwise the slides are correct. The worksheets for each chapter is posted as quizzes on Brightspace. Your answers need to be submitted to the quiz. The homeworks will be problems from the book and submitted to assignments on Brightspace or turned in during class. And the exams will be multiple choice exams in here. Our textbook is OpenStax Astronomy. It's available for free at openstax.org. I already showed you how to access it on Brightspace, but you could either go to the syllabus, textbook, and schedule and follow the link to the textbook here, or there are links in each individual chapter to that chapter of the textbook. Homework. So the worksheets for each chapter are posted on Brightspace. Your answers are submitted in the quizzes. The homeworks are problems from the book. Submitted to assignments on Brightspace or turned in during class. So if you go to homework and worksheets, Here are all the worksheets for the first set of worksheets. They're just quizzes on Brightspace. This is the homework. These are the problems you need to do in the book. And how you can find them. These are the exercises. I put page numbers, but if you're using the website, there are these questions at the end, review questions, thought questions, at the end of each chapter. So for like chapter 2, go away. Here are the review questions and then the thought questions. And you can see the numbering continues. So you can use those. Those are the questions you're going to do for the homework. So if you have the chapter 2 exercises, it's the ones at the end of each chapter. They're review questions and thought questions. I believe all of them are review questions and thought questions, though maybe some of them will be figuring for yourself, but I don't think I actually used any of those. And the exams will be multiple choice and in class. And there'll be 4 of them, and they'll each be on a section of chapters. So there's not going to be a comprehensive exam on everything at the end. We're just doing 4 exams on each section of chapters. And lastly, after the last exam, we will be doing the presentations for the semester project. That's how I have the schedule set up. Who just called me? I'll just leave this. They can call me back. That might have been IT. The semester project, you need to turn your topic in by October 9th. And the report is a 2 to 3 page paper on your topic. And the presentation is a 5 to 10 minute presentation on your topic of PowerPoint. It's like 6 to 15 PowerPoint slides. And then this is the schedule. So are there any questions? As always, if you have questions, you can always email me. The best way to contact me is email. And also I'll just always be here after class. Oh yes. And this is important. At the midterm, there are certain requirements you have, otherwise you will be automatically dropped from the class. You need to demonstrate that you're doing active pursuit. You need to have submitted, you need to have completed all exams, and submitted at least half of the homework and worksheets. You don't have done good on them, you just have to have done them. And if you haven't met the academic pursuit standards by the midterm, you will be dropped. It's not like difficult. It's just, this is basic standard you have to. Again, you don't have to do good on those, you just need to submit them. I mean, you should try and do good. And I do accept late work. So that'll count towards active pursuit. And I mean, if it's something came up and there was like, you missed the last exam, but you've already set up a plan for retaking it or something, I'll take that into account and you won't get dropped. I have flexibility on this, but that's the requirement. That is the thing you should be trying to meet. So, welcome to Astronomy. We're going to start with a sort of general overview of astronomy and science. So, what is astronomy? Astronomy is basically the study of everything above the atmosphere. It's the study of the universe and everything in it. So things like planets and moons, asteroids and comets. Your name?
Joseph.
Last name? Stars, galaxies, nebulae, black holes, and more. So planets, comets, stars, galaxies, nebulae, black holes, more. Well, hello, Cooper. So, one of the advantages of studying astronomy and other sciences is it teaches a way of thinking, right? It helps you learn how to critically analyze information, how to apply this to everyday situations, and it gives you a broader understanding of the universe and your place in it. So the way we gain a better understanding of the universe scientifically is through scientific thinking. So here are some definitions for some terms. A theory. When a scientist says something is a theory, it needs to be something that is testable, and it's based on observation and study. So something like the moon is made of green cheese is a hypothesis. But if it turned out to be true, that would be a theory. If you were able to test it and support it with evidence. Obviously, the moon is not made out of green cheese. The moon is made out of very expensive rocks. Well, they're very expensive because they're from the moon, but the moon is made out of rocks. So a model is a simplified representation of how things work. In general, when scientists use the word theory, there's a little whiffiness, but when someone talks about a theory of something, they're talking about something that's held up generally under evidence and is based on observations and experiments. Before that, you start with a hypothesis. You start with an idea, something you think might be the case. So this is a proposed explanation. And then you test it by either making more observations, doing an experiment, something like that. So a proposed explanation for some observation. We see the sun rise in the east every day, therefore the sun must orbit the Earth. This is what people thought was the case for thousands of years. And it took a long time to figure out that that was not actually the case, that the Earth, in fact, the sun didn't orbit the Earth rotated, which is why the sun appeared to rise in the east every day. Come on. So the scientific method starts with an observation. It never really ends. From a philosophical point of view, the scientific method is based on essentially radical doubt. Everything is always testable. Some things are better supported than others, but the general idea is you make some sort of testable prediction, you come up with a hypothesis to explain your observation, and then you test this prediction. This can be either by excuse me. making more observations, setting up an experiment. If the predictions are found to be correct, then that's great. Then you can make more predictions and continue testing, continue experimenting, get a better idea of how things happen. If the predictions are found to be incorrect, oops, you have to modify or redesign your hypothesis. And sometimes what you find is that your predictions are correct. A somewhat common thing that's happened through the history of science is we have some model or way of making predictions, and it is correct most of the time, but sometimes it doesn't work. So it's incomplete, effectively. So this is what's led to things like special relativity and general relativity. They handle or quantum mechanics. They handle extreme situations that are different from what our previous models handled at some level. But they do have to generate everything our previous model did because those work under normal conditions. So it's a cycle. You're constantly refining your knowledge. You make observations, you think of interesting ideas, you formulate hypotheses, you develop testable positions, you gather data to test those predictions, you either refine, alter, expand, or reject those hypotheses. And then you can develop general theories and feed back into the whole cycle. In astronomy, everything is very far away from us. So most things have to be done by observations, and a lot of stuff has to be done somewhat indirectly. But there are certain advantages to it as well. Because if we want to know what the past of the universe looked like, well, we can just look, because it turns out light takes time to travel. So if we look at things far enough away, they're from the past. Now, astronomy, because we're dealing with the whole universe, we will be looking at very big and very small numbers. So numbers need to be expressed. To deal with this, we have a tool called scientific notation. Basically, the distance from the Earth to the Sun is 150 million kilometers. So you can write that as 150,000,000, which is big, and all the zeros start to blur together. Or you can write it as 1.5 times 10 to the 8th. And that 10 to the 8th basically tells you how many digits there are in the number. And that's really useful in astronomy because a lot of the times things vary in size on the scale of like the numbers you're interested in. A lot of the time astronomers are only interested in being right to within an order of, within a factor of like 10. So astronomers, a lot of the time, don't even look at this number. They just look at the little number of the exponent. And so to convert a number to scientific notation, you move the decimal point until there's only one number to the left and count the number of places you've moved. If you had to move the decimal point to the left, that's a positive exponent. Positive number exponents are big numbers. Negative exponents are little numbers. There's not going to be much calculations in this class, but I will be expressing values in scientific notation. So just general piece of knowledge. Positive number in the exponent, that's a big number. Negative number, that's a little number. Because we will be dealing with numbers on the scale of like 10 to 30. I'm not writing 30 zeros. All the measurements in this class are going to be in metric units. Using the meter for length, the second for time, and the kilogram for mass. Science is just done in metric units. We will also use some additional units once we get to scales that are so big where even the metric unit, using large metric units is awkward. So eventually we'll be measuring distance in things like light years, which is the distance that light travels in a year. and mass in things like solar masses, which is how many times the mass of this object is compared to the sun. But scientific measurements are all made in metric units. All American customary units are in fact defined in terms of metric units. And all our units can be derived from these. So things like velocity and density, etc. Now, distances in astronomy get really big. So the nearest star is 440 trillion kilometers from the Earth. Notice how many zeros there are. We can write it as 4 times 10 to the 13, but that number is just so big you can't think about it. Once numbers get big enough, the human brain just, they're all big. So what astronomers do is that they develop units that work better for those scales. So for measuring large distances, astronomers use the light year. For measuring distances in the solar system, they tend to use the astronomical unit. The light year is the distance that light travels in 1 year. Because light travels at a fixed speed, it's 100,000 kilometers per second. It's 3 times 10 meters per second. I mean, there's an exact number. It's like 299.7 something. It's an exact whole number because we actually define the length of the meter based on the speed of light. A light year is the distance that light travels in about a year. It's about 10 trillion kilometers. So in light years, the nearest star is a little bit over 4 light years away. We still can't probably comprehend the distance because it's so outside of this human scale, but we can deal with numbers more easily. But the light year is far too big to be used in the solar system. For example, Earth is 8 1/3 light minutes away from the sun. So we use the astronomical unit to measure distances of the solar system. And the astronomical unit is just the distance from the Earth to the sun on average. Because the Earth's orbit isn't perfectly circular. It's a little bit closer some parts of the year. It's a little bit further other parts. It's actually closest in January and furthest in July. It's the average distance between the Earth and the sun. It's about 150 million kilometers. So at this scale, Mars is about 1.5 astronomical units from the sun, and Neptune is about 30 astronomical units from the sun. And this is much easier to comprehend. Like it's easier to deal with distances on the scale of a city in miles than in feet or in inches. 1 mile is easier to deal with than 5,280 feet or 63,360 inches. And these definitions, again, make the numbers more manageable. Another reason for the astronomical unit, for a long time, we knew the distances to all the other planets in the solar system in terms of the distance of the Earth to the sun, but we didn't know the exact distance from the Earth to the sun. It turns out we were able to figure out the relative distances of everything, but we didn't have a great way of measuring exactly how far away the Earth was from the sun. One of the very interesting things is that, as we mentioned, light takes time to travel. What this means is you're always looking at the past. And in astronomy, this gets more severe. So for example, if you're looking at something about, I don't know, light takes about a nanosecond to travel a foot. So if you're looking like at someone 10 feet away, that's from about 10 nanoseconds ago. Actually, it's longer than that because your brain takes more time than 10 nanoseconds to process things. But that's how long the light took to travel. So the light from the sun takes about 8.5 minutes to get to Earth. Actually more like 8.3. Hold on. The light from Alpha Centauri, which is the nearest star to us, takes about 4.3 years to get to us. And the light from the Andromeda Galaxy takes about 2.5 million years to get to us. The Andromeda Galaxy is one of our nearby galaxies. It's like the nearest large galaxy. So we see the sun as it was 8.5 minutes ago. We see Alpha Centauri as it was 4.3 years ago. And we see the Andromeda Galaxy as it was 2.5 million years ago. What this means is that if you look back, you look far enough away, you can see further and further back into the history of the universe. And in fact, we can look back far enough to the point where we see essentially the burning fireball of the Big Bang. And that is the cosmic microwave vacuum. It's cooled down effectively, but you can look back far enough to the point where the universe was okay. So we never see any object as we see it as it is right now. When we look out into space, we're looking back in time. And this means that astronomers have this really interesting advantage that other sciences don't have, where we can literally look at the past. We can't look at the past nearby, we can look at the past. Everybody else has to figure out what happened in the past from what's right now. But astronomers can just look at the past. We can look at stuff from 13 billion, well, yeah, from like 12 billion years ago. Yeah, it's emitting light. That light is, I mean, it's just, okay, so these days we're not looking at it with eyeballs directly. But you could. So these telescopes, there's no reason you couldn't direct the light that's coming out of one of these telescopes to a human eye. It's just that directing it to a camera is much more convenient and better. And it would be hard for a human eye to see some of these things because they're so big. So if we use a camera, we can expose it for a very long time, things like that. But yeah, it's just the same light. It's coming from that object, bending through some lenses or bouncing off a mirror, but well, usually bouncing off a mirror, but it's still the light that came from that object. So yes, you're not usually looking at it directly with your eye. It's just for practical purposes, cameras are so much better than human eyes. I mean, you can, there's still some biggish telescopes out there that you can look at stuff through. And if you have a telescope, you can see things. You're not going to see something from billions of years ago because those are so faint, they're just hard to see. But you can see things from millions of years ago. You could get a telescope and look at the Andromeda Galaxy. It's not that hard. And all the stars you see in the sky are, you're looking at stuff that's, no, most of the stars you see are still alive because they have lifetimes in the billions of years and they're not that far away. Or millions of years and they're not that far. Most of the stars you see in the sky are not that far away. Closer things are brighter. Though mostly what you see are actually really, really bright stars. And those are relatively short-lived. But most of those still aren't that far away because the galaxy just isn't that big. So here we're gonna watch a quick video showing the scale of various things. We'll start on Earth and zoom outwards to the edge of the universe. And then we'll look at the very small. I think that's how this video is set up. And hopefully this works. Oh, why is this not doing things? Um, So the universe is pretty much empty. There is a lot of empty space. If the sun were the size of a basketball, the Earth would be a pea about 100 feet away. Everything out in space is real empty, and like things we think of that like look like clouds are millions or billions of times less dense than the atmosphere in this room. There's just a lot of them. So, sun the size of a basketball, the Earth would be a pea about 100 feet away. The nearest star would be a few thousand kilometers away. And there is basically nothing between the stars. I mean, there's like loose gas and stuff, but it's atoms per centimeter. Few peas and specks of dust in the solar system. And our solar neighborhood would be a dozen or so basketballs, each of 2,000 kilometers. Space is very empty, which is why we can see things from very far away. Because if you look in the right direction, nothing's in the way. So astronomy has made enormous progress in the last 100 years or so. So the big thing that happened was we got our modern understanding of gravity. Like, our understanding that there were galaxies outside of our own is only about 100 years old. And things like that. So general relativity is our modern understanding of gravity, put together by Einstein. And it's a little over 100 years old. Published in 1910-ish. Around then. We did special relativity first and then general relativity. Special relativity is easier than general relativity. It's called special because it's a special case and not the general case. And then we're going to go through some of the discoveries in the last 100 years or so. So in the 1920s, Edwin Hubble was able to determine that the Andromeda Nebula is actually a galaxy like our Milky Way. So 1923 was when we first truly understood that there were other galaxies than our own. And Edwin Hubble was able to determine that there were other galaxies. He had the biggest telescope. He was using the biggest telescope in the world. And he was able to determine other things about them that were very important. We'll get later on this. And 1925, Cecilia Payne-Spoken determined that hydrogen is the most common element in stars and therefore the most common element in the universe. Hydrogen makes up roughly 75% of everything by mass. That's a rough number. And then in 1929, Edwin Hubble, by observing these things he determined were other galaxies, and collecting data on all of the ones he could find, was able to determine that the universe is expanding and that more distant galaxies are receding faster. And this was known to be a possible solution to general relativity. And in fact, Einstein put in some math to make sure the universe was a steady state constant. And said that that was his greatest mistake when Hubble discovered that the universe was expanding. And the big deal about the universe expanding is that that was the point where we discovered that the universe, if the universe was expanding, then it used to be smaller. So eventually it had to have started somewhere at some point. Like, that setup of the universe is changing and is not something that was the same forever. In 1930, Cloud and Combo discovered Pluto. In 1932, Karl Jansky detected the first radio waves from space, opening up the field of radio astronomy. Radio astronomy is one of the more important fields of astronomy these days because radio waves go through a lot of stuff. It turns out because they're nice and long, they don't get affected by a lot of small things. So they let us see things we would not be able to see otherwise. And then in 1933, Walter Bead and Fritz Zwicky described the neutron star that would form in a supernova collapse. Pretty sure that's the Crab Nebula. There is a neutron star in the middle of it. This is the remnant of a large star dying violently. It blew up and left behind this nebula. And that supernova was actually observed. We have records of it happening. It was in like 1000 AD or something, but we have Chinese and Japanese records of the supernova happening. And then in 1938, Hans Bethe described the method of nuclear fusion that powers the stars. We gained the understanding of nuclear fission and nuclear fusion around then. This led to other somewhat less fortunate discoveries, like how to efficiently turn cities into not cities. But you know, we began to understand how the stars were powered. In 1948, the Palomar 200-inch telescope was completed. This was the largest telescope in the world for 3 decades. There's an image of it. Had a 200-inch mirror. In 1957, Sputnik 1 was launched. This was the start of the space age. And then people started exploring the moon. Luna 2 and 3 explored the moon. They crashed into the surface and imaged the far side of the moon, respectively. This was the first time people had images of the far side of the moon. Because it turns out the moon, the same side of the moon always faces the Earth. So when you look at the moon at night, you're always seeing the same side. The phases of the moon are just the shadow of the moon on itself. It's not fully illuminated, but you're always seeing the same side of the moon. And in 1961, we had the first humans to orbit the Earth. Yuri Gagarin. Was it Yuri? Oh, I can never keep track who actually managed the first orbit. Yuri Gagarin was the first to space, but I can't remember if he was the first to orbit. In 1962, Mariner 2 became the first craft to move to another planet. It went to Venus. Venus is actually the closest planet to Earth. Also in 1962, Martin Schmidt discovered that quasars, which were these weird bright objects we saw, were actually active galaxies, and therefore were the most distant things, the most distant objects known in the universe at the time. So these quasar stands for quasi-stellar radio source. They looked like stars because they were like single bright points, but the frequencies they were emitting didn't make sense. And what Martin Schmidt did was discovered that actually they did make sense. They just had to be, they were incredibly redshifted. We were moving away from us incredibly fast. So they were super, super far away. In 1965, Arno Penzias and Robert Wilson discovered the cosmic microwave background, which is that last echo of the Big Bang, is the way you can think of it. It is literally the light of the fireball of the Big Bang. And that was discovered by accident. They were basically, see that radio telescope back there. They were basically going through and eliminating all these sources of noise, and they had this one source of noise that wouldn't go away, no matter which way they pointed their radio horn. And they checked everything. It wasn't their equipment. It wasn't pigeon poop. And they eventually realized, no, there is actually this signal that is coming from everywhere in the sky. And it corresponded with what people had calculated the echo of the Big Bang to be, once they actually were able to like measure it in some detail. It's a ridiculously perfect match. Like as we get more and more detailed, it's kind of insane how accurate our model is for what we see. Luna 9 had the first soft landing on the moon. The Luna probes were all Russian. 1967, Jocelyn Bell discovered the first pulsar. She was doing radio astronomy, discovered a really strange, really regular repeating signal, and was able to figure out that it was a pulsar, which is a star, which is a neutron star emitting radio waves, but it's spinning very fast, so it emits radio waves in a beam that swipes past us repeatedly, like a lighthouse. 1968 was the first manned flight to the moon. 1969 was the first manned landing on the moon. In 1970, Uhura was the first X-ray satellite launched to detect X-rays and other short wavelength light. You have to go above the atmosphere because the atmosphere will just absorb them. In 1971, Salyut 1, the first space station, was launched. And over time, more space stations have been launched and deorbited and such. And currently, there are 2. In 1972, Charles Thomas Bolton identified Cygnus X1 as a black hole. Black holes which don't emit any light are, you'd think they'd be hard to see, but it turns out the stuff falling into them emits enormous quantities of light. And so you can see that. But Cygnus X1 is a black hole. This was determined by, it's in a partner, it's a binary star with another star. They're orbiting each other. So we were able to determine that this thing they couldn't see that was emitting X-rays, that's what the X part of the name means. They were able to figure out its mass from the orbit of the other star. And it was basically too big to be anything but a black. In 1970, but a proper image of a black hole didn't happen until a few years ago. But we have now successfully taken a picture of the stuff falling into a black hole. It was ridiculously hard. 1975, Minerva 9 sent back the first image from the surface of Venus. That, I'm pretty sure is, oh yeah, that is an artist's impression. Because the Minerva pictures are, they look like strips of rocky ground. And then the probe dies. The last Minerva probe that lasted the longest lasted maybe 2 hours before it was destroyed by the conditions on Venus. In 1976, the Viking landers landed on Mars. And the search for life was unsuccessful. This has been more or less this summer yeah. We don't find life when we go to Mars. We find evidence that conditions were such that there could have been life in the past, because we found very clear evidence that there was like running water on Mars. There was water on the scale that you could have life happening in it. But we've never found any direct evidence for any life existing on Mars or having existed. So the most likely case for Mars is that if life existed on Mars, it existed in the past and it's all dead. Voyager 1 and 2 in 1977 were launched to explore the outer solar system. Voyager 2 visited, and both of those are still active. We're still in communication with both Voyager 1 and 2. There's a website you can go see the current status of them. They still have some working instruments. Every once in a while, we lose contact with them if something goes wrong, and you get these articles about issues with Voyagers. They're old, and they're in interstellar space. They're beyond the area dominated by the sun. Both. Voyager 2 visited all 4 of the outer planets: Jupiter, Saturn, Uranus and Neptune. Voyager 1 only visited Jupiter and Saturn and headed off towards interstellar space. Whoops. So Voyager 1 is the furthest man-made object from the universe. It's like 130, 150 astronomical units away. There's a website, you can look at the exact number, because it's being tracked. And the rings of Uranus were discovered in 1977. You were not discovered by the Voyager probes, because they hadn't gotten there yet. It took a long time to get out to Uranus. But they were actually discovered when Uranus went in front of a star, and there was a pattern of the star dimming from the rings, and it repeated on the other side. The problem with Uranus's rings, they're hard to see because they're very faint. They're thin and dark. Unlike Saturn, which has shiny, highly reflective wide rings. In 1978, Vera Rubin was able to confirm the existence of dark matter. Most of the matter in the universe is dark matter, which we know very little about, other than it exists, it's dark, it doesn't really interact with anything else except by gravity. And it makes up about 80% of all the stuff in the universe. Well, all the matter in the universe. Stuff might be a more general term, because it turns out there's also another thing called dark energy, which we know even less about. We'll get to that. In 1983, IRAS was launched. This is the first satellite to study the sky in the infrared. Infrared doesn't work on Earth because A, the atmosphere absorbs it, or B, the ground is emitting infrared. You are emitting infrared. So you have to go stick your thing out in space. Now, the James Webb Space Telescope is a primary, U1 is a primarily infrared telescope. As it turns out, we want to look at stuff from the very early universe. Infrared light is a little more useful because of redshift. Things that are far away are moving away from us fast, and that means the light from them gets stretched out, so they end up redder. In 1986, Voyager 2 visited Uranus. And in 1989, it visited Neptune. Voyager 2 is the only space tube to have visited Uranus or Neptune. The problem is just they're so far away. In 1990, the Magellan spacecraft mapped the surface of Venus with radar, giving us our current accurate maps of the surface. Because you can't look at the surface of Venus, because Venus is permanently covered in clouds. Why it's so bright in the sky, because they reflect a lot of light, but it's permanently covered in clouds. In 1990, the Hubble Space Telescope was launched. And it is still working to this day, which is kind of amazing considering how many things on it have broken. And that it was designed to be modifiable and repairable, but it was designed to be modifiable and repairable by the space shuttle. And we don't use the space shuttle anymore. But yeah, a bunch of things on it are actually not working, have broken over the years. So they've had to do workarounds. But it's still getting great data, well past its intended lifespan. In 1992, the Cosmic Background Explorer was able to detect ripples in the background radiation of the universe. So that's that echo of the Big Bang. We were able to detect tiny variations in it, which you're looking at a map of there. And by studying those tiny variations, we can figure out things about the structure of the entire universe. In 1992, we had the first confirmed detection of an exoplanet, the first confirmed detection of a planet around a star other than our sun. And we've found thousands of them since. Well over 5,000. And in 1998, construction began on the International Space Station. So this is one of the two space stations that is in orbit around the Earth right now. There is also the Chinese space station, whose name I cannot recall off the top of my head. And then in 1998, we discovered dark energy. Because it turns out, not only is the universe expanding, the rate at which it's expanding is speeding up, and that needs to be something needs to be doing the pushing, and that is dark energy. And that's pretty much all we know about dark energy. Very little is known about dark energy. Now, something that caused a big deal, in 2005, Mike Brown discovered the dwarf planet Eris in the outer solar system. And the thing about Eris is that Eris was another thing out beyond Neptune that was heavier than Pluto. It was more massive than Pluto. And they'd found a number of other similar objects around the same time. So in 2006, the International Astronomical Union finally formally defined what a planet was, because it turns out there wasn't one, a formal definition, and what a dwarf planet is, and also what a minor planet is. But and at that point, that was when Pluto stopped being a planet and started being a dwarf planet. And there was a lot of hoopla about it because people were emotional about it. In 2012, Subi Gazari got the first visual proof of the existence of black holes. Still indirect, but not quite as indirective as oh yeah, it was a flare from a black hole. In 2013, the first extrasolar asteroid was discovered. So this is the first asteroid that we know came from outside our solar system and was passing through. In 2015, New Horizons explored Pluto and gave us a whole bunch of fascinating images and information about it. Also in 2015, LIGO finally managed to detect gravitational waves. And this is a big deal because this is the first time humans were able to detect things out in the universe with something other than light. Because before this, everything astronomers had used was in some way light. And there's radio waves and X-rays and such. They're all light. They're all the same thing. But gravitational waves are different. So that's the signal from the first gravitational wave detection. Hilariously, it happened like a day after they started the run. They were not expecting it to happen so quickly. And a number of gravitational wave incidents have been detected. 2017, the first time the source of a gravitational wave, which in this case was a neutron star collision, was identified in optical and other wavelengths. So this is the first time people were able to detect the gravitational wave and get a picture of the thing with light at the same time. And this is tricky because the events that generate gravitational waves are short. They don't last forever. They're neutron stars colliding or black holes colliding with each other. So this doesn't happen over a long time. These are, if we look at time scale on this, these time scales are seconds, and this whole time scale is less than a second. I mean, the light it's emitting is gonna last longer for a neutron star merger, but yeah. You had to get a telescope pointing in the right direction real quick, or have it had already been. So you had some sort of sky, I think we got it from some sort of sky survey that was sort of looking for funny things that happen. And they were able to correlate them. And that is all for this lecture. You have any questions? Okay. So please try and make sure you get here. Stop sharing. I'm gonna end the meeting. I got you for attendance, Cooper.